Good morning. We're going to get started. It takes me a while to get used to being back in school again. I left my pens in my car, so hopefully I won't do that again. All right, I hope you had a great weekend. We left off last time talking about bonding. And we have two kinds of bonding. We have ionic bonding and covalent bonding. We were talking about ionic bonding. Are there any questions before we get started? I want to see a quick show of hands. I'd like to, on Wednesdays, try to integrate some active learning activities into our class on Wednesdays just to see how it goes. I want to try a bunch of different things, and then I want to give you a survey at the end to see what you liked. First of all, I want to see a show of hands of anybody who does not have an iClicker. You all have them. Okay, so we're going to be trying a couple of different things. There are some programs now where you can actually draw compounds on your smartphone. Is there anybody who does not have a smartphone or an iPad or laptop? A few of you. So what I would probably have you guys do is work with the person that's next to you. And we'll do some group activities, and as long as we stay on time in the class, we'll continue to do that every Wednesday. All right. Okay, so let's get started. All right, so we were talking about ionic bonding. Atoms attain a filled shell by transferring electrons from one atom to another. So our classic example is lithium fluoride. So lithium transfers its single valence electron to fluoride. That makes lithium happy because now it has a full shell, and it makes fluoride happy because fluoride has a full shell. And these guys are held together by electrostatic interaction in a crystal lattice. And that's your actual ionic bond. The electrostatic attraction between the positively charged species and the negatively charged species, that's your ionic bond. Ionic bonding is seen with atoms of widely different electronegativities. And so back in GChem, you learned metal and nonmetal. And there's other things that are not metals and nonmetals. So that's not strictly true. But the reason that's true is because the electronegativity difference from things on the left-hand side of the periodic table are very different than the electronegativities on things on the right-hand side. So one of the periodic trends that you learned in GChem that you will absolutely need to know here is that we increase electronegativity going to the right. And we also increase electronegativity going in this direction. And I'll just abbreviate that EN for increasing electronegativity going in that direction. So that leaves fluoride with the largest electronegativity. And basically, in general, if electronegativity difference between the two atoms is greater than about 1.8, so let's write that over here. In general, it's right here. Electronegativity difference is greater than about 1.8. The electron will be transferred completely, and the bond will be an ionic bond. There are some exceptions to this rule, but that's a good general rule here. All right, so that's ionic bonding. Let's talk about covalent bonding. Atoms attain a filled shell by sharing electrons. Most of the compounds that we talk about in organic chemistry have covalent bonding. And so here's an example here. We have two hydrogens, and these would be hydrogens that you just plucked right off the periodic table. So they both have unpaired electrons. And so they come together, and they both share electrons. Each hydrogen is happy because it has 2 electrons in its valence shell. That would be a filled shell for hydrogen. And then this hydrogen is also happy because it has a filled shell. It has 2 valence electrons. Even though they're sharing them, both hydrogens have a filled valence shell. And so we usually write that bond as just a line. So here's my equivalent symbol here. We have hydrogen, hydrogen. So there's a hydrogen-hydrogen covalent bond. So each hydrogen shares 2 electrons. And so each hydrogen has the helium configuration. So that would be a covalent bond between like atoms. We can also have a covalent bond between non-like atoms. So we could have hydrogen combining, for example, with a chlorine. Straight off the periodic table again. And they could each share 2 electrons. They're going to combine. Hydrogen's going to share 2 electrons with chlorine. Chlorine, because hydrogen donated electron, now is sharing, it now has 8 electrons in its valence shell. Hydrogen now has 2. So both atoms are happy. So hydrogen has 2 electrons, and chlorine has 8. So they both have filled shells. This type of bonding is seen with atoms of the same or closer electronegativity. So for hydrogens, 2 hydrogens combining the same electronegativity, hydrogen and chlorine, pretty different electronegativities, but we can have all kinds of covalent bonding. So let's look at how hydrogen, carbon, nitrogen, and oxygen and the halogens satisfy the octet rule. And so carbon has 4 valence electrons. It needs 4 more to fill its shell. And so it's going to make 4 bonds in with neutral carbon. It's going to make 4 bonds. Nitrogen has 5 valence electrons, so it needs 3 electrons, and so it's going to make 3 bonds. It's going to make 3 bonds, and it's going to have a pair of non-bonding electrons. I want to emphasize the neutral here because we also work with a lot of charged compounds in OCHEM, and so this is neutral. Neutral nitrogen has 3 bonds and a pair of non-bonding electrons. Oxygen has 6 valence electrons. We need 2 to complete the shell, so oxygen is going to make 2 bonds, and it's going to have 2 pairs of non-bonding electrons. So this is what we will commonly see with neutral oxygen. Hydrogen can only make 1 bond. It needs 1 more electron, so to make that 1 more electron, it's going to make 1 bond. And halogens, here's an example here. Chlorine, let's just do chlorine. Let's put some atoms here. Chlorine has 7 electrons. It needs 1 electron, so it's going to make 1 bond. So here's an example here for each of these. Hydrogen, oxygen with 6. Nitrogen with 5. And carbon with 4. So when you draw it that way, you can see that it's really easy to see that carbon here. Oh, we have the, what's going on here? Oh, I'm sorry. This light needs to go off. Did not notice that. Let's do video mute. Is that better? Okay, sorry about that. You'll have to let me know when that happens. I didn't notice. All right, so when we draw it like that, you can see that carbon needs to make 4 bonds to make a full valence shell. Nitrogen has to make 3, so these unpaired 3 electrons are what it's going to use to make new covalent bonds. Oxygen needs 2, hydrogen 1, and chlorine 1. Okay, so an easy way to remember this is it's called the HONC 1, 2, 3, 4 rule. Hydrogen and halogens make 1 bond, oxygen makes 2 bonds, nitrogen makes 3 bonds, and carbon makes 4 bonds. And again, this is for neutral compounds. I want to strongly emphasize that. For neutral atoms. Questions so far about covalent bonding? All right, so that's neutral compounds. What happens when we have charged atoms? That's for neutral atoms. What about charged atoms? or charged atoms or charged molecules, the number of bonds change. So carbon normally has 4 valence electrons when we take it right off the periodic table. When carbon is positively charged, it only has 3, and so in order to when carbon is cationic, it's going to make 3 bonds. And so notice we have no octet on carbon, and we call this a carbocation. So no octet on carbon, carbocation, and so when we see carbon that's positively charged, it's going to have 3 bonds and an incomplete octet, always. So number of bonds to atom when ionic, so carbon with a negative charge is going to have 3 bonds and a pair of non-bonding electrons. So we call this a carbanion. So we have carbocations and we have carbanions. Nitrogen has the number of bonds to neutral atom 3. When it's cationic, it's going to have 4 bonds. When it's anionic, it's going to have 2 bonds and 2 pairs of non-bonding electrons. For oxygen, number of bonds to neutral atom, we have 2. When it's cationic, we have 3 and a pair of non-bonding electrons. So this would be similar to hydronium ion, which you're already familiar with. When it's anionic, it has 1 bond and 3 pairs of non-bonding electrons. All right, so a couple different approaches to understanding why this is. Approach number 1, you can just memorize this chart. That's certainly one way to do it. Another way to do it is, if you don't like memorizing, I don't like memorizing, is how can I understand what's going on here? How can I understand that a carbocation has 3 bonds, a carbanion has 3 bonds and a pair of non-bonding electrons? So let's look at that. So we have neutral, let's look at carbon. We have neutral carbon, has 4 electrons in the valence shell. All right, so if we have carbon with a positive charge, that means we have one of those electrons is gone. Now carbon only has 3 electrons in its valence shell. So this is what, if we drew electron dot structure here, this is what a carbocation would look like. And so you can see that that carbon can only really do 3 shared bonds because it has 3 unpaired electrons here. So it can only bond to 3 atoms. All right, carbon with a negative charge, on the other hand, neutral carbon has 4 electrons. Carbon with a negative charge is going to have 5 electrons. All right, so that's negatively charged carbon. And you can see that it's got 3 spots to share an electron pair. And so it's going to make 3 bonds. So this bonds to 3 atoms. So bonding like in nitrogen. Bonding like in neutral nitrogen. So let's put this back up for a second here and take a look at that. So see nitrogen here. We're going to overlap a little bit. Hopefully you could see both of those. Neutral nitrogen looks like this. So this is isoelectronic with neutral nitrogen. It's got 3 spots for making bonds, just like nitrogen. The only difference here is that this is negatively charged, and certainly it's not nitrogen, it's carbon. All right, oxygen, let's do O+ here. All right, so oxygen normally has 6 electrons in its valence shell, but we have 1 less because it's positively charged, so we have 5 electrons. So oxygen with a positive charge is going to look it's going to have the same number of valence electrons as carbon with a negative charge and nitrogen with a neutral charge. And you can see when you do that, that we're going to make 3 bonds also. Bonds to 3 atoms, like C minus and nitrogen. Let's do one more. You could do this also for nitrogen. Let's do oxygen with a negative charge. Okay, so oxygen, normally oxygen straight off the periodic table has 6. It has a negative charge, so we add an electron, right? So it's going to have 7 electrons. So it's going to be like a halogen, isn't it? It's going to bond like a halogen. It's going to make 1 bond. So this one bonds to 1 atom. So it's kind of a big deal. One of the things that's very different about OChem is that we are very concerned about where charges are in the atom. So in GChem, you would draw a molecule, and if the molecule had an overall charge, you would put the brackets around it and put the charge outside the brackets. We don't do it that way. We put the charges on the atoms. So if we have a molecule that has a positive and a negative charge in the molecule, and so no net charge overall, we put the charges on the atoms. So we don't ever put the charge outside of brackets. So really big deal about what the charge is on an atom based on how many bonds and how many non-bonding electrons. That's a big deal here. And so however you want to do this, you just want to memorize the charges here, you want to memorize them here, but I can tell you that the points that you miss with not doing charges correctly, they'll add up a lot. And I still see students in 51C getting charges wrong. So if you want good insurance for yourself, you're going to learn the charges right away. And that will really help you. So it's very second nature to you all quarter. And so what I invite you to do is when you get your first midterm back, you start keeping a tally of how many points you've missed because you didn't have the right charges. So it does add up. It's a big deal. So this is really important and completely different than GChem in this respect. All right, exceptions to the octet rule. 3rd row and higher elements. These have d orbitals available for bonding, so they sometimes exceed an octet, not all the time in their valence shell. And we don't deal with too many compounds like this, but the 2 things that we do use, sulfuric acid and phosphoric acid. So we have sulfuric acid here. We have phosphoric acid here. Not even so much phosphoric acid, but we do work with potassium-containing compounds. And so because these are 3rd row or higher elements for our central atom here, they can exceed the octet very easily. So oxygen here has an octet. All the oxygens have octets. Oxygens, anything in the 2nd row cannot exceed an octet, but sulfur can. This oxygen here has an octet. Has to, 3rd row. Sulfur, on the other hand, has how many electrons? 2, 4, 6, 8, 10, 12 electrons. And that's okay because it's a 3rd row. And we'll see coming up why that's okay to have that for sulfur when we talk about orbitals. We'll see that coming up. Phosphorus has, remember, 2 for every bond, 2, 4, 6, 8, 10. 10 electrons. Again, okay because it's a 3rd row element. All right, so that's one exception to the octet rule. Yes, question?
Why is it that on the phosphoric acid, one of them is OH and the other one separated with a bond?
That's the structure of phosphoric acid. There's several resonance structures. We're going to get to resonance structures coming up, but that's generally the way we draw that. Okay? We've got 3 hydrogens to account for, so 3 of those oxygens are bonded to hydrogen. And so if we had a double bond here, that would make positively charged oxygen, and that could be a resonance structure, but it's not one of it's not the best resonance structure for phosphoric acid. Okay? Any other questions? Yes? Oh, right here. Is this what you're talking about? Okay, yeah, you know what? You're right. We're going to talk about that coming up. We do little shorthand things in OCHEM, and once you've done it, it's hard to not do it. And so that's what I just did. Thank you. So you're not even going to bat an eye when you see that later on, because we're going to talk about shorthand ways of drawing. Thanks for clearing that up. Yeah. All right, so exception number 1, molecules, atoms that are third row and higher elements. Molecules with open shells, sometimes there are not enough electrons to provide an octet. So boron's our famous example, which you probably saw in GChem a number of times. This can make 3 shared bonds. So this is just like something we just looked at, right? What did we just look at that looked like that? Carbocation, right? So yeah, so this is like a carbocation. The difference is the carbocation has a positive charge, but it's the same situation. So this can make 3 shared bonds. So one of the famous compounds that we have that boron really likes to combine with is fluorine. So we have, and I'm just going to draw these in a different color so you can see what's going on easily here. It's going to combine with 3 fluorines. When it does that, you can see, though, that boron only has 6 electrons in its valence shell. So we call this an open shell compound. And we're going to see carbon as an open shell compound. Right now it looks really strange to you, but we use carbon. Carbocations are very, very common intermediates in organic chemistry, so that's a common example in organic chemistry that you'll see. Open shell compounds can accept a pair of electrons to complete an octet, so one of the things you might remember from, and we're just going to draw this with bonds now. One of the things you might remember from GChem is compounds with open shells like to accept a pair of electrons. So this is a common reaction for boron trifluoride. And I'm going to use an arrow here. This is going to be our first arrow. We're going to see more arrows in chapter 2. But what that's telling me is that I'm just taking those 2 electrons from nitrogen and donating them to boron. Anybody remember what this type of reaction is called from GChem? Lewis acid-base reaction. If you don't know that, not a big deal. We're going to talk about that in chapter 2. But that's a Lewis acid-base reaction. So once that happens, boron has a negative charge and nitrogen has a positive charge. Now, since overall that's a neutral molecule in GChem, you wouldn't have put those charges on those atoms. But we do in OChem. We want to know exactly where all the charges are on each atom. All right, so new covalent bond here. And now boron has an octet. So we're going to see the same type of reactivity with carbocations. Carbocations open shell just like boron. So only 6 electrons in the valence shell, just like this. And what we're going to see with carbocations is carbocations also accepting a pair of electrons from another molecule. Questions so far? Anybody? Yes?
Are you putting the positive minus in just because of the polarity?
This is a formal charge on boron and a formal charge on nitrogen, and we're going to talk about that coming up. How you calculate that, how you figure that out. Okay? All right. Representation of structure. There's a Lewis structure, which is what I've been drawing so far. Lewis structures give connectivity and the location of all bonding and non-bonding electrons. So when I ask for a Lewis structure on the exam, you need to include all the bonding and all the non-bonding electrons and any formal charges on any atoms. Again, we're going to talk about how you calculate that coming up. They don't show actual 3D arrangement of atoms in space. So that's the nice thing about Lewis structures. We don't have to worry about three-dimensional orientation in space. So we know for a fact that in boron trifluoride, we don't have 90-degree bond angles. We just don't. Nor do we have 90-degree bond angles in ammonia. But if it's a Lewis structure, that doesn't matter. We can draw it any way we want. We can draw any bond angles we want, because Lewis structure doesn't show orientation in three-dimensional space. There are ways to represent that we'll talk about coming up. To draw Lewis structures, use the traditional method. See page 13, 3rd edition, or page 14, 4th edition. Follow the Honk 1, 2, 3, 4 rule for neutral compounds to maximize the number of bonds without exceeding the octet rule, and assign formal charges to any charged atoms. So I know you drew a lot of Lewis structures in GChem. It's actually a little bit easier here because in GChem you pretty much had the whole periodic table you had to think about. We just use a very small bit of the periodic table. So it makes it a little bit easier for us to draw structures. What's different is that in GChem you always had a central atom. We don't always have a central atom here. So you kind of have to look at each atom as you go. So I'm going to work some examples so you can see how to do this. So any way that works for you is what you're going to use. I don't make you do this a certain way. So you can use the traditional method. You could do the Honk 1, 2, 3, 4 rule, or a combination. So whatever works for you. And what you're going to find is that after a while, you're going to know how to draw things without going through a whole rigmarole to figure out how many electrons you have. Just by using the Honk rule and just getting used to certain structural features in molecules, you'll be able to do it without going to a lot of work here. So for example, draw the Lewis structure for CH3Cl. There's 2 ways to do this. Find the total number of valence electrons of all atoms and arrange pairs of electrons around each atom to give each an octet. If any atom does not have an octet, use a lone pair to form a double bond. So this is kind of the GChem way that you used to do this. So let's do that. Carbon has 4 electrons, 3 hydrogens. So 3 times 1 electron per hydrogen. Chlorine has 7 electrons. So we add those all up, 14 electrons. All right, so we have carbon. We actually do have a central atom in this particular example. We're just not always going to have that. We've got 3 bonds to hydrogen. That would be 2, 4, 6, 2 for every bond. Bond to chlorine, that would be 8. And we certainly are going to have some lone pairs on chlorine. 2, 4, 6, 8, 10, 12, 14. Okay? so that everything adds up. We've got all our electrons, everything has an octet. Hydrogen doesn't have more than one bond, we're good. Definitely, I want to emphasize, don't forget to draw all non-bonding electrons on Lewis structures. Don't forget to draw all non-bonding electrons on Lewis structures. We're going to learn some shorthand ways of drawing things, and when we do the shorthand ways, we're not required to put lone pairs, but on Lewis structures we are. So that's point number one. Point number two, don't use lines for lone pairs. All right, so the way that you would draw this in GChem, and we don't want to do it this way. Yes, it's faster, but it's a problem here. And it's a problem in OChem because, so that would be lines for lone pairs. So if you haven't done that before, this is going to be easy for you. And I'm off the screen here. If you haven't done that before, this is going to be really easy for you. But you see the problem here when we start dealing with things like chlorine? Sometimes students will leave off a lone pair, and if they leave off a lone pair, then is that a chlorine or is that a carbon with a pair of non-bonding electrons? The other thing is when we're doing charges, we have, like, say we have atoms with a negative charge. So is that a non-bonding electron or is that a charge? And the other thing is we're going to be doing things with arrows when we're doing mechanisms coming up. And you might have an arrow going to this molecule, and that pair of non-bonding electrons might look like part of the arrow or not. It just gets too confusing. So I don't want you to use lines for lone pairs in this class. So that's maybe a hard habit for you to break. All right, so here's a shortcut. So that's sort of the GChem way. Shortcut is to use the HONC 1, 2, 3, 4 rule. And that's that we know that carbon makes 4 bonds, and hydrogen and chlorine 1 bond each. And so carbon's going to make 4 bonds. So 1 bond to hydrogen, another bond to hydrogen, another bond to hydrogen, another bond to chlorine. And then certainly chlorine needs its lone pairs to make an octet. So that would be a faster way to do that. And you really are going to get to a point where you won't even have to think to draw methyl chloride. You won't have to count electrons. You won't have to do any of that. That's where we want to get. So it makes it a lot easier for you. Let's try ethylene. So CH2, for ethylene. All right, so we've got 2 carbons. So 2 times 4 equals 8 electrons. We have 4 hydrogens. 4 times 1, and that equals 4 electrons. So we've got 12 electrons altogether. We don't have a central atom here. So we're going to have the 2 carbons here. This is a shorthand notation we're going to talk about coming up. It's a condensed structure. Each carbon is going to be bonded to 2 hydrogens. Okay, so let's count electrons. 2, 4, 6, 8, 10. And 1 carbon is getting a lone pair, 1 is not. So if we have an unpaired electron, we're going to try to make a bond to get rid of that unpaired electron. Because carbon doesn't have an octet. This carbon does. And so we're just going to kind of move that over like this. That gives us this structure. And as you can see, carbon is making 4 bonds. Each carbon makes 4 bonds. Each hydrogen makes 1 bond. And so that's what ethylene looks like. Now, ethylene does not have right angles in its structure. So I know for a fact that we don't have right angles here, but that's okay. It's a Lewis structure. We can draw things any way we want in Lewis structures. Don't have to draw the correct angles. All right. So this can also be done with the Honk rule. We know that carbon has 4 bonds. Each carbon has 4 bonds. Each hydrogen has 1. So in order for this carbon to have 4 bonds, it has to have a double bond between the 2 carbons. So that's another way to look at that. All right, now we're getting increasingly difficult to here. Now we have something that has a charge, and so we're going to draw a Lewis structure for this compound that has a positive charge. And I would recommend, if you're drawing a structure that has a charge, overall charge, that you don't use the Honk rule, that you actually count electrons. Because especially at the beginning, it's going to be difficult for you to draw and to know that you have the right number of electrons. All right, so we have 2 carbons. And I'll just do it right underneath. So that's 2 times 4 electrons. We have 5 hydrogens. 5 times 1. We have 1 oxygen. So that's 6 electrons. And don't forget to account for the charge. If we have a positive charge, that means we have 1 less electron, right? So on positive charge, minus 1 electron. And if you add that all up, it's going to be 18 electrons. All right, when we are drawing, I want to make a strong point here. When we're drawing Lewis structures, we are only doing even electron pairs. We're not doing any unpaired electrons with these. So make sure when you add up your electrons that this number is an even number. If it's not, you've done something wrong. You've forgotten to account for charge or counted something wrong. So 18 electrons. If we forgot that charge, this would be 19 and we would know something was wrong. Okay? All right, so let's draw this here. Carbon here. This carbon is bonded to 3 hydrogens because of the way it's drawn in the condensed structure. And I'm going to show you that coming up. This carbon here, the second carbon is bonded to 1 hydrogen. And then we have oxygen, which is also bonded to a hydrogen. So there's sort of the skeleton. Now let's count up electrons because we have some extra electrons we have to place here. 2, 4, 6, 8, 10, 12, 14, 16, 18. Now I put those on oxygen because I just naturally put those on oxygen because it's more electronegative. Okay, oxygen is more electronegative than carbon. So we have to make decisions on where to distribute electrons because we don't really have a central atom. Which atom is central here? So I put them on oxygen because oxygen is more electronegative. So when you were doing this in GChem, you distribute the electrons to the outer atoms, right? First, before you did the central. And I put them on oxygen because I know that oxygen is more electronegative. All right. Could have drawn it that way. But notice carbon only has 3 bonds here. So we actually could have drawn it. You might have drawn it a different way here. And this is another way to draw it. This carbon with 3 hydrogens. And we have this carbon bonded to 1 hydrogen. We're concerned that this carbon only has 3 bonds. So let's make that carbon with 2 bonds. So, and let's count electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18. So that would be another way to draw that. And that looks better because all atoms have octets in that molecule. But there is more than one way to draw this. And so I want to make some points about this example here. Before you turn the page, let's do I'm going to put this up here, but you don't need to turn the page yet. A formal charge must be assigned to any atoms that have a formal charge. Do we have any atoms with a formal charge in this first way of drawing that? Carbon, right? Carbon with 3 bonds has a positive charge. And that's if you've memorized that chart. But we know carbon has 4 bonds. And so if carbon doesn't have 4 bonds, it has a charge. Okay, so we know that. Oxygen likes to make 2 bonds by the Honk rule. So it doesn't have 2 bonds, it has 3. That means it's going to have a charge. And so if you've memorized that chart, then you would know that this has a positive charge. All right, so formal charge must be assigned to any atoms that have a formal charge. So these structures would not be complete without the charge. Formal charge indicates deviations from neutrality, and it's a way to locate the charge on an ion. So formal charge, if you calculate it, is number of valence electrons minus half the number of bonding electrons minus the non-bonding electrons. That's the formula for calculating it. Do you remember that from did you have something like that in GChem? Okay, so that's the same formula. And you also know from GChem that the sum of all the formal charges in the molecule must equal the overall charge. So let's calculate that. Now I'm going to save you some time here with the Honk rule. We're going to go back and calculate that positive charge. So that's in case we don't have that chart memorized. We would need to calculate this charge. So I'm going to save you some time here. Do I have to calculate a formal charge for any of these hydrogens? No, because they're bonded to one atom. So I will see some people on the exam calculate formal charge for every single atom. If it has the right number of bonds and it has the right number of non-bonding electrons, you don't need to calculate. It won't have a charge. Does this carbon have a formal charge? No, it's got 4 bonds. This oxygen here, does that have a formal charge? No, it's got 2 bonds. So it just leaves, we're just left to this carbon here. So let's calculate that. All right, carbon has 4 valence electrons. And we subtract half of the number of non-bonding electrons. Carbon has no non-bonding electrons. So that's minus, half the number of bonding electrons. So half of 6. It has 0 non-bonding electrons. And if we calculate that, it's plus 1. Now we leave the 1 out. So 1 is understood. So don't write plus 1, just write plus. Okay? If it's 2, then we would write it. But 1 is understood. And then let's go ahead and do oxygen here. Oxygen has 6 valence electrons. It has 3 bonds. So it's going to do half of 6. And it's got 2 non-bonding electrons. Minus 2. And that's equal to plus 1. So each of these molecules here, each of these ways of drawing this, both have a charge, and that's good because the overall charge of this molecule is positive, and both of these have a positive charge. So that means we've done really well. Okay. All right, I'm going to show you another way to do this without using the formula. Yeah, question?
Would it be incorrect to do it like you count how many electrons it came with and how many it has at the end?
That's what I'm going to show you right now. So I think he reads minds a little bit here, in the front here. Okay, so here's another way to do it. Because you know what? When you're nervous taking an exam, it's easy to make a math error just doing this calculation here. All right, so carbon normally has, straight off the periodic table, has 4 valence electrons. It owns, for the purposes of formal charge, it owns 1 electron from each of these bonds. Okay? So it owns 1, 2, 3. It's supposed to own 4, so that means it's down 1 electron. It has a positive charge. Is that what you were talking about? Okay, same thing, oxygen, 6 valence electrons. It owns all of its non-bonding and 1 from each of these bonds. 1, 2, 3, 4, 5. It's only got 5. That means it has a positive charge. So that's another, so I've given you 3 ways to do this. Memorize the chart, use the formula, or just look at how many electrons that atom actually owns. And when we look at how many electrons that atom's own, that's exactly what we're doing right here. Okay? All right, so that's point number one. Above molecule can be represented by more than one Lewis structure. We've got two here that are possible. They are resonance structures for the same molecule. So these two are resonance structures. All right. We're ready to turn the page now. All right, so I just redrew this to save us a little time. If we wanted to do arrows, we can show how to go from this resonance structure to this one, or from this one to this one. To go from this resonance structure to this one, we're going to use an arrow that looks like this. It's going to come from the non-bonding electron pair, and we're going to go right here. We're going to move that pair of non-bonding electrons. We're going to make a new bond between carbon and oxygen. So there's the new bond. So notice what we've just done here. We've moved this pair of electrons. We're making a new bond here. So now over here we have a new bond, new covalent bond, and we only have one pair of non-bonding electrons now. Okay, so that's and so we can go back and forth. If we wanted to go the other way, Sapling has you go the other way. They have you go each way. So let's go the other way too. To go from here to here, we would just reverse that arrow. We're going to come from this bond, and we're going to go here over to oxygen. That would go back and forth from each of these resonance structures. All right, so what we've done is we've done something called a curvy arrow, and that's something new that you didn't use in GChem. Curvy arrows are like right here, and that shows movement of a pair of electrons. Fishhook arrow shows movement of a single electron. So this looks like exactly like a fishhook. So this shows movement of a pair, and this shows movement of a single. We have a reaction arrow. We have all different arrows here. We have reaction arrow. There's also equilibrium arrow, which you should remember from GChem. Equilibrium arrows going back and forth. And then we have resonance arrow. They all mean something different. We want to make sure that we use the right one. So this one right here is a resonance arrow. And the other two here are curvy arrows. And so the brackets indicate resonance structures here. So again, rather than having the positive charge on the outside of the brackets, we actually have it on the various atoms that it belongs to. So these two structures here, I want to make a point about this. We have two resonance structures. These two resonance structures are not going back and forth from each other. All right, that would be if they were going from this resonance structure to this one and back to this one and back to this one, we would use equilibrium arrows. We're not doing that. We're using resonance arrows. So the true structure of this molecule is a hybrid of those two resonance structures. It's not 50% this and 50% this. It's sort of a weighted average, whichever one is better, which we're going to talk about coming up. And there's sort of, it's a hybrid of the two. So we only have one true structure. We can draw that structure. I want to emphasize first, they are not in equilibrium. And let's try to draw the hybrid really quick. I'm not sure which clock is right. I've got a clock up here, and I've got this clock. Who knows the real time? It's 9 what? It's 9:51. We'll draw the hybrid next time.